Box plots are a great way to represent or summarize a single column of numbers, especially those with many data values. It is quick to calculate. Take a column of data and sort it from low values to high values. The middle point in the vector is called the median. The data value at 25% of the way down is called the first quartile, and the data value at 75% of the way down is the third quartile. And by definition, another name for the median is the second quartile. Now the distance, or length, between the third and first quartile is called the interquartile range, or IQR. Take the number at the third quartile and subtract it from the number at the first quartile. That difference is the interquartile range. So far, we have three numbers that now summarize that data column: the first, second, and third quartile. The median gives an idea of the average, and the interquartile range gives an idea of the spread. It is important to realize these three numbers are three actual values from the data vector. They are not calculated. Imagine you have measured the temperatures on a cold day in Canada once every minute over a period of 8 hours. What might be an approximate value for the interquartile range? Now imagine you measure the temperatures once per day over a period of 1 year. What would the IQR value be approximately for this vector? How does the IQR value compare to your first one? You can see now why the IQR is a helpful measure of spread. Statisticians call this dispersion. A box plot is a way to show these three numbers graphically, as well as that spread. There are two other features shown on a box plot: fences and outliers. Two fences are always shown. The first fence is calculated at quartile 1 minus 1.5 times the IQR. You can see it over here. The second fence is on the other side, at quartile 3 plus 1.5 times the IQR. Fences are calculated values, so they are hypothetical boundaries. Unlike the first, second, and third quartiles, they don't necessarily correspond to actual values from the column of data. Points that lie beyond the fences are called outliers. These outliers are often shown as circles that lie outside the fences. It is useful to consider what the box plot would look like for a vector of data that came exactly from the normal distribution. Real data are almost never this nicely balanced. Now let's look at a box plot from an actual data set that I've worked on before. When lumber is cut in a modern sawmill, the tree trunk is scanned with lasers, and the optimal number of cuts and positions are determined by a computer. The blades cut along that path, and after the board is cut, it is measured for quality control at 6 positions. The target thickness is 1680 in this example. Here are 6 box plots, one for each position on the board. The box plots show the thickness using data from the most recent 100 boards that were cut. Pause the video and study the plot. What do you notice about the sawmill's operation? What recommendation would you give to improve the process quality? It seems like all the boards are close to the target. The dark black line inside each of the box plots, the median, is close to the target 1680 value for all 6 positions. That is desirable. But position 1 seems to be creating a high degree of outliers with a large deviation from the median. These are boards that are sometimes too thick and sometimes too thin. Something in the process is causing unexpected variability. Maybe there is a problem with how the lumber is leaving from the blades. Notice the asymmetry of the IQR in the first box plot. It is skewed towards higher values. These boards are leaving slightly too thick, which might cause customer complaints later on. As enrichment, we'd like you to look up and research the violin plot. It is a variation of the box plot that superimposes the histogram distribution of the data on top of the box plot.